an AI-generated post for your viewing pleasure. Researchers have uncovered the stunning versatility of mercury-cadmium telluride, a semiconductor that can transform its electronic structure on demand, and use this shape-shifting superpower to generate mind-bending nonlinear optical effects at terahertz frequencies. The findings could pave the way for a new generation of ultrafast optoelectronic devices. Imagine a semiconductor that can drastically alter its electronic properties with the simple turn of a dial. That's the remarkable reality of mercury-cadmium telluride, HgCdTe, a material that has captivated scientists for decades with its ability to seamlessly transition from a semimetal to a semiconductor and back again. Now, a team of researchers has harnessed this chameleon-like behavior to uncover the material's extraordinary potential for ultrafast nonlinear optics at terahertz frequencies, a frontier that promises to unlock new frontiers in sensing, communications, and more. By probing HgCdTe's shape-shifting electronic structure, the researchers have not only revealed the inner workings of this unique semiconductor, but also laid the groundwork for a new class of terahertz devices with unparalleled capabilities. At the heart of the researchers' findings is the intimate relationship between HgCdTe, electronic band structure, and its nonlinear optical response. By carefully tuning the material's band gap, carrier concentration, and electronic dispersion through temperature changes, the team was able to toggle between two strikingly different regimes of nonlinear terahertz dynamics. At low temperatures, where the band gap is small, the nonlinear response is dominated by the process of Zener tunneling, the quantum mechanical tunneling of electrons between the valence and conduction bands. This leads to a marked reduction in the overall terahertz transmission, as the material generates a surge of free carriers that absorb the incoming radiation. But turn up the heat, and a whole new world of nonlinearity emerges. At room temperature, the band gap widens and the electronic dispersion becomes more parabolic, suppressing Zener tunneling. Instead, the nonlinear response is driven by the quasi-ballistic motion of charge carriers, which can transiently boost the terahertz transmission by modifying the material's electronic polarization. Remarkably, the researchers' simulations reveal that this ballistic nonlinearity is intimately tied to the unique shape of HgCdTe's conduction band, one that becomes asymptotically linear at high energies. This allows the electronic polarization to saturate at high field strengths, leading to a highly nonlinear, yet persistent, response that persists long after the terahertz pulses have passed. The team also uncovered slower, picosecond scale dynamics in the nonlinear response at high temperatures, which they attribute to possible interval scattering or carrier relaxation processes. While not fully captured by their model, these findings point to the rich complexity of HgCdTe's ultrafast behavior. The researchers' work builds upon a growing body of research exploring the unique properties of semiconductors with linear or nearly linear electronic dispersion, such as graphene and topological semimetals. These materials have shown a remarkable capacity for strong nonlinear optical interactions, driven by their gapeless band structure and massless charge carriers. However, the present study marks the first time that such effects have been systematically investigated in the terahertz frequency range for HgCdTe, a material whose electronic structure can be dynamically tuned to mimic the properties of these exotic systems. By uncovering the delicate interplay between HgCdTe's band gap, carrier concentration, and band shape, the researchers have opened up a new frontier for exploring ultrafast nonlinear optics in narrow-gap semiconductors. Importantly, the findings also challenge some previous assumptions about the role of impact ionization in driving nonlinear terahertz dynamics in HgCdTe. While earlier studies had suggested this mechanism was dominant, the current work indicates that it is likely a minor player compared to Zener tunneling and ballistic transport, at least under the experimental conditions studied. This discrepancy highlights the need for a more comprehensive understanding of the various carrier generation and recombination processes in these materials, and how they depend on factors like pulse duration and field strength. The researchers' work provides a valuable roadmap for navigating this complex landscape, with important implications for the design and operation of terahertz-based devices. The researchers' exploration of HgCdTe's shape-shifting electronic structure has yielded a remarkable trove of insights into the material's ultrafast nonlinear optical properties. By demonstrating how small changes in the band gap and carrier concentration can dramatically alter the nature and magnitude of the terahertz response, the team has unveiled the exquisite sensitivity of this semiconductor to its electronic environment. The ability to toggle between Zener tunneling-dominated and ballistic regimes, simply by tuning the temperature, suggests intriguing possibilities for dynamically controlling the nonlinear optical behavior of HgCdTe. And the findings on the role of the material's unique conduction band shape in governing the ballistic nonlinearities could inspire further efforts to engineer the electronic structure of narrow-gap semiconductors for optimal nonlinear performance. Beyond these fundamental insights, the researchers' work also holds important implications for the design and operation of terahertz-based devices. With carrier generation, scattering, and relaxation processes playing a central role in nonlinear response, understanding and manipulating these dynamics will be crucial for realizing the full potential of HgCdTe and related materials in sensing, communications, and other emerging terahertz applications. As the field of ultrafast nonlinear optics continues to push the boundaries of what's possible, the shape-shifting semiconductor at the heart of this study stands ready to reveal even more of its extraordinary secrets. With the researchers' roadmap in hand, the path forward is clear. Unlocking the full potential of this chameleon-like material could lead to a new generation of terahertz technologies that push the limits of what we thought possible.